Hello everyone and welcome. In our lesson today, we're going to be looking at normalization of floating point numbers. Normalization is mainly used to maximize the precision for a given number of bits. So in this case, we start looking at the behavior of our mantissa and our exponent. The key role of the mantissa here is that the more the mantissa we have, the better the accuracy of the number we're working with. And the more the exponent, the more the number we can store. Now, one thing I would like you to note is that in normalized form, there is only one non-zero digit before the decimal point. There's only one non-zero digit before the decimal point. So if you look at what I've written down here, when working with positive numbers must be represented during normalization process as 0.1, and then you can have other values, whilst negative numbers must be represented as 1.0. What I found is that when students understand this key point here, then it makes a lot more sense when they're solving problems. Let's say, for example, we have numbers written as not 1, 1, 1, 1, not 1, 1. Let's just assume that we have our decimal point here. The idea here will be to shift the decimal point to the left until you hit a non-zero point, where before we start having recurring zeros, and then you stop. Again, if the number you're working with is 1111.0. Now let me do it this way. 1101111.01. The aim is to shift the decimal point, if it's a negative number, to shift the decimal point up to this point here. So you can see a positive number here is 0.1, and negative number is 1.0. This probably doesn't make sense now, but when we start solving problems relating to normalization of floating point numbers, I hope it will make sense to you. So let's look at our first example. In our first example, we're going to normalize the floating point number 3.25. So technically, we would have to first represent this number to its binary form. We have looked at how floating point numbers can be represented to binary. You might want to check my other videos that I've posted online. So 3, we know that 3 is 1, 1. I'm going to make it 4 bits. So I know that 3 is 0, 1, 1. Okay. And I know that 0.25 is 1 over 4. So 0.25 is 0, 1. Again, I'll make it just 4 bits after. So that's 1, 2. That's 1 over 2, 1 over 4, 0.25. Okay. Now, looking at this number here, to normalize this number, the aim will be to shift the decimal point. Because it's a positive number I'm working with, I'll want to shift the decimal point to the left, in this case, until I hit the 1 before I just move beyond the 1 before the recurring zeros. So I'll move my radix point to the front of this number 1 before the recurring zeros, so to the left. I've moved it 2 places, 1, 2. So because I've done that, I now have 0.110100 times 2 to the power 2. Now, in the exam, you will be told the value of your mantissa and the value of your exponent. In this case, I will be making use of a 10-bit mantissa. My mantissa will be 10-bit and my exponent will be 6-bit. So to represent my mantissa in 10-bit, I'm going to have not 1 1, not 1, not. So that's 1 2 3 4 5 6 7, and I'll balance it out with zeros. For my 6-bit exponent, the value of my exponent is 2, and I know 2 is 1 0, and I'll just balance it out. 1 2 3 4 5 6. So 3.25 in its normalized form is not 1 1, not 1, all zeros, and then its exponent is not 1 not. In our second example, we are going to normalize minus 0.3125. Again, the first thing we would have to do is to represent 0.3125 in its binary form. Because it's a negative number, we will then convert it and represent it to its 2's complement form. So, one way of converting numbers like this to binary is to multiply the fractional bit there by 2. So what you can do is you can actually say 0.3125 times 2. Now 0.3125 times 2 gives us 0.625. Okay, so I'll take the 0. So it gives us 0.625. That's 0 there. That's what I have there. So I'll multiply 0.625 by 2. Now 0.625 by 2 gives me 1.25. So I'll put the 1 there, and then I'll just say 0.25 times 2. So 0.25 times 2 gives me 0.5, and I'll put the 0 there. And here I would say 0.5 times 2. 0.5 times 2 gives me 1.0. Gives me 1.0. And if I say 0.0 times 2, gives me 0. So this is how you actually can get binary numbers from fractional using in floating point numbers. Okay, so to express this now, what I have is 0. So I write down the 0 point. Now for 3125, I'll take the decimal point in this order. So I'll have 0, then I'll have 1, then 0, then 1, and then 0. Okay, now let's not forget that this is a negative value here. So there's a negative value here, and it doesn't matter. I could have more leading zeros here. It doesn't matter. So having this value, it means I have to now represent it in its 2's complement form. To do that, I'll flip my 1s to 0s and 0s to 1. So I'm going to have 1.1010111, and if I add 1 there, I would have 0 carry 1, 1 plus 1 is 0 carry 1, 1 plus 1 is 0 carry 1, 0 plus 1 is 1, then I'll have 1, 0, 1.1. Do not get confused because I've added more zeros there. It doesn't matter. If I add another 0 there, I'll still have 0, 0, 0, 0, 1, 1. The same thing applies here. If I add more zeros, more leading zeros here, it means I'll still just have 1, 1, 1 down here, and if I bring them down, I'll still have 1, 1, 1. It doesn't matter. So at this point, I know that to have, if I'm working with a negative number, negative numbers I know must be represented as 1.0. So I get rid of all the leading ones. So in this case, there is no need for these leading ones. I want to shift my decimal point up to this point here. So technically, from what I have here, that is 1111.10110000. I need to move my radix point. I need to move my radix point up to there, just one place. Okay, and if I do that, because I'm shifting this time my decimal point from the left hand side to my right hand side, it means that just to one place, it means that my exponent is going to be a negative number, -1, -1, because I'm moving from the left hand side now to the right hand side. So this means that I have 1.011000 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2 to the power -1. I would have to represent -1 in its 2's complement form, and we know that -1 in 2's complement is all ones. If you don't know how I've got that, if we have -1, and we're using a 6-bit exponent, we know that first to get 1, that's 1. If we flip the 1s and 0s, it gives us that in its 1's complement form. And if we add 1 to put it in its 2's complement form, we have all ones. Okay, so -1 is that's the value of the exponent. So this means our final answer is 1, 0, 1, 1, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's our mantissa, our 10-bit mantissa, and our 6-bit exponent is 1, 1, 1, 1, 1, 1. That's our final answer. Okay, so something to pay attention to is, first, learn how to convert your fractional numbers to binary, and by just multiplying by 2, you should be able to solve that. And another thing you must remember is, if the decimal point is shifting from the left hand side to the right hand side, our exponent becomes a negative value. If it's shifting from the right hand side to the left hand side, our exponent is going to be a positive value. Okay. In our third and final example, we're going to look at normalizing the floating point number minus 4.5. So the first thing you want to do is you want to represent 4.5 in its binary form. So 4.5 in its binary form, I know the number 4 can be represented as not 1, not point. So remember our number sequence here, we have 1, 2, 4. So that's the binary representation. And the number 5, and I know it's half, which is 1. So 0.5 there is half. Now I'm going to do something here. I'm going to make this longer. I'm just going to add leading zeros there. Okay, so this means I have more bits to work with, which is absolutely fine. It will not affect your answer. If you want to, you can add more leading zeros here. It doesn't matter. It will not affect your answer. So having done this, I would now have, because this is a negative number, I would have to represent it in its 2's complement form. To do that, I would have to flip the zeros to 1s and the 1s to zeros. So technically, I would then have 1, 1, 0, 1, 1, point, not 1, 1, 1. Once I've done this, it's now in its 1's complement form. To its 2's complement form, I'm going to add 1. So if I add 1 to this, it means I'll have 1 plus 1 is 0 carry 1. 1 plus 1 is 0 carry 1. 1 plus 1 is 0 carry 1. 0 plus 1 is 1. Then I'll bring down the rest of the values that I have here. With all of these now, the next thing I would want to do is, you can see here, this is where I have my decimal point here. I would want to now shift my decimal point to the front of the number 1, the front of the number 0 before the recurring 1s that I've got. So let's not forget that if I had zeros here, multiple zeros there, I would have 1, 1, 1 here, which means in the final answer here, I'll have 1, 1, 1 here. So I would have multiple recurring 1s here. So the idea here is to normalize this point, to move my radix point to the 0 before the recurring 1s. So if I do that, I'll then do shift 1, 2, 3. So I've shifted 3 places to the left. So I have 1, that's that 1 there, point 0, 1, 1, 1, 0, 0, 0 times 2. Now, because I have shifted my decimal point 3 places to the left, my exponent is going to be a positive value. So this is going to be 2 to the power 3. 1, 2, 3. 2 to the power 3. So writing my answer now, in 10-bit mantissa, I would have 1, 0, 1, 1, 1, 0, 0, 0. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as a 6-bit exponent, my exponent is 3. And 3 in binary is 1, 1. Because it's 6-bit, I'll just add 4 zeros there. So this is our answer in 10-bit mantissa and 6-bit exponent. okay.